Hi, everyone. Hope you're all having a fantastic Thursday. Mine is pretty chaotic. Sometimes I really wish I were a kid again. I miss the carefree summers of just nothing but carefree frolicking. But unfortunately, I don't really have much of that anymore. I have to do grown up stuff because I'm a grown up, I'm told. So, this is a part two to the integration by parts video I submitted yesterday. I posted that on YouTube yesterday. And we covered just some basic integration by parts problems, just so we have a really good understanding of how the process works. So in this video, we're going to be covering two really specific cases of integration by parts problems. And by the way, if I randomly run off, it's because my pizza is ready. And clearly I have a really, really good sense of priority. My priorities are where they need to be. So in this video, we're going to be working on two specific problems that focus on two individual, really special cases of integration by parts integrals. And you'll understand what I mean in just a second when we get started on the first problem. But first, I want to just remind you what the formula is to solve an integral using integration by parts. So it's going to be the reverse of the product rule for derivatives. We're going to need something in this form, the product of two different things. So if we're given the integral of u dv, that's going to be equal to u times v minus the integral of v times du. So, like I said, this is going to involve some really special cases of integration by parts. So the first case we're given is going to be something like this, or it's going to be exactly this. We're going to have x, let's make it x cubed times e to the x dx. And at first, it doesn't look anything out of the ordinary. It looks completely simple. It looks ordinary. It looks like something we dealt with yesterday, but this one is actually a really special one. You'll see why in just a few minutes. So remember that our first job, when we're given an integration by parts integral, is to choose a u and to choose a dv. So either we're going to have this be u and then everything else is going to be dv, or it's going to be the other way around. So remember that whenever we're choosing a function to assign to be u, we want the function that gets simpler when we take the derivative to be u. We have two choices. We have x cubed and we have e to the x. So when we take the integral, or when we take the derivative, when we take the derivative of e to the x, we just keep getting e to the x over and over again. But when we take the integral of x cubed, why do I keep saying integral? When we take the derivative of x cubed, we get 3x squared. When we take the derivative of 3x squared, we get 6x. When we take the derivative of 6x, we get 6. And then, of course, the derivative of 6 is just 0. So out of these two, we can tell that the function that gets simpler when we take the derivative is going to be x cubed. So we're going to have that be u. And then we're going to just have everything else that's not part of x cubed be dv. So we have our u right here. And we have our dv is everything else in the integral. So we have half of the information we need now. Let me resize this a little bit and move it out of the way. I feel like we're going to need some extra room. So we have u, we have dv. We want to start by writing everything down. So u is going to be u is going to be x to the third, x cubed. So we're going to take the derivative and then multiply both sides of the differential equation by the dx in the denominator of du. So we get 3x squared dx. All right, and then we want to write down dv as well. So we know from the original expression that dv is equal to e to the x dx. So then v is going to be the antiderivative of dv. So v is going to be just simply e to the x without the differential, without the dx. All right, so we have everything we need. So now we're going to substitute everything into the formula. So this is the integral of u dv. It's going to be equal to u times v, but I want to didn't mean to do that. I'm going to resize this a little bit first and just make it clear that it's not part of the actual problem we're doing. It's not part of the integral itself. It's just supplemental information we need to actually solve the integral. So we're going to have u times v first. So u is x cubed. and v is going to be e to the x. So this is going to be, uv is going to be e to the x times x cubed. You could put it in any order you want. Doesn't really matter. And then we have minus integral of v times du. So v is e to the x, and then du, we can see du is equal to 3x squared. So I'm going to move the 3 out front just to make things a little easier to conceptualize. So we have minus 3 times the integral of e to the x times x squared. So it looks like we have to use integration by parts again. We know that because we have the product of something and something else. We have something that gets simpler when we take the derivative, which would be x squared, and then we have something that doesn't get simpler when we take the derivative. E to the x just remains the same when we take the derivative over and over again. So we're going to have to do integration by parts once again. So we are going to write it like this. It's going to be e to the x times x cubed minus 3. And then instead of writing this integral, I'm going to put brackets to show that we're doing another iteration of integration by parts. So once again, we're going to choose another u, and we're going to choose another dv. So between these two, e to the x and x squared is the one that gets simpler when you take the derivative. So let's have this be u. And naturally, everything that's not part of u is going to be dv, which means this dx is also going to be part of dv. So the double underlines are part of dv. The single underlines are part of u. So the derivative of u with respect to x is going to be 2x times dx. dv is all the double underline parts in the integral. That's going to be e to the x times dx. And then the antiderivative of e to the x is e to the x. So let's go ahead and substitute everything in. So I put brackets around this entire integral right here. We're going to replace the integral with uv minus the integral of v du. So we have uv is going to be x squared times e to the x. And then minus the integral of v times du. So v is e to the x. Du, we can see, is 2x dx. So we're getting somewhere at least. We're going to have to simplify this a little bit more and then do another iteration of the integration by parts. So I'm going to move the 2 out front just to make things a little easier to handle. So our integral becomes this. And I'm going to just simplify things a little bit. I don't like having multiple sets of nested brackets, so I'm going to distribute the negative 3. So we're going to have e to the x times x cubed minus 3 times e to the x squared and then when I distribute the negative 3 to the integral, it's going to make, we're going to have a plus 6 on the outside when we distribute that negative 3 to the negative 2. So we're going to have plus 6 times whatever that integral happens to be. And then I'm going to put the x first, x times e to the x dx. Almost there. I think we have to do at least one more iteration of integration by parts, which means we're going to have another u and another dv. So between x and e to the x, the thing that gets simpler when we take the derivative is going to be x, which means we want everything else to be dv. So we have u is equal to x. Everything that's not part of that is going to be dv. So e to the x dx is going to be our dv factor. Next up, we want to take the derivative of x to get du. The derivative of x is just 1, so that's going to turn into 1 dx. The antiderivative of e to the x is still just going to be e to the x. So let's substitute in everything. So we're going to have plus 6 times, it tells us we're going to have uv minus the integral of v du in brackets. So uv is going to be x times e to the x. And then we have minus the integral of v times du. So that's going to be e to the x times dx. Now, notice how this one is one that we can integrate without any special techniques, without integration by parts. We know exactly how to integrate this. So I'm going to distribute, and I'm going to be really lazy. I'm going to distribute this plus 6, but I'm just going to remove the brackets and then adjust things where necessary. So if we distribute it to the first term, this is going to turn into 6x e to the x. But if I distribute it to the second term, it's going to turn into a minus 6 times whatever the integral is. So now we are in good shape. We have one more integral to do. So it's going to be e to the x times x cubed. My handwriting is really bad today. Minus 3 times e to the x squared plus 6 times x times e to the x. And then we have the antiderivative of e to the x is still going to be e to the x. So we're going to have minus 6 times that antiderivative. 6e to the x plus c is our final answer. So this is what we call the general solution. A general solution is always going to have a constant of integration because we don't know what if there was a constant there initially, and if there was, we don't know what the value of that constant is. So if we don't have a constant, it's called the particular solution. If we do have the constant there, if we do have the plus c, we call that a general solution because it refers to not just one solution, but actually a family of solutions, a family of functions that satisfy this. All right, so we're going to focus on the next special case of integration by parts now. So in this next really special case of integration by parts, we are faced with something that doesn't look like it even really fits the mold of what we're trying to do here. We're used to having a situation where we can choose a function that gets more and more simple when we take the derivative. But as you guys can see, we don't have any of those functions that match that description. So neither of these really get simpler the more we take the derivative. You might be tempted to think that we really can't do integration by parts here. We're going to have to either run away in terror or find some other way, Wolfram Alpha or something, to integrate this. But there is actually a way to use integration by parts to solve this integral. And it's not super obvious at first why I'm making things the way they are, why I'm making the choices, why I'm making them. But as we go on and solve this problem together, it'll become more and more clear why I'm making the choices that I make. So I'm going to have u be cosine of x. And I'm going to have everything else be part of dv. So that includes the e to the x and the dx. That's going to be dv. So the the derivative of cosine of x is going to be negative sine of x times dx. And then just like with the last problem, the antiderivative of e to the x is still going to be e to the x. So now is when we want to start substituting things in. So this is going to be u times v minus the integral of v times du. I'm going to put the negative sine of x first for simplicity reasons. So that's going to be v times du. We're going to have an e to the x, and we're going to have a negative sine of x. All right, so I'm going to simplify this a little bit. We have minus a negative. That's going to turn into a positive. So we're actually going to add the positive version of this integral and get the same result. So as you guys can see, we're going to need to do this once again. We're going to change up our values. So the dv and the v are going to remain the same. I'm still going to have this entire thing be dv. So I'm only going to change the u and the du. I'm going to leave everything else the same. So, pizza's ready, guys. Be right back. Sorry, guys. It's really unprofessional of me, but Pizza is really, really important. It's a huge force in my life. So hopefully you can understand the circumstances. All right, so we left off by using one iteration of integration by parts to rewrite this. So remember the concept of modularity. Modularity is the process of breaking up a big problem into multiple smaller pieces that are more manageable. So that's what we're doing here. We broke up this one integral into two pieces, and we're going to continue breaking this up until it's something we know exactly what to do with. So I'm going to do another iteration of integration by parts. So I'm going to just write what we have so far. E to the x cosine of x plus, and then I'm going to do another iteration right here. So we're going to choose a u, and we're going to choose, well, we already have dv and v chosen. So u is going to have to be sine of x. And if we take the derivative of that, we get cosine of x times dx. And then after that, we're going to plug things in. We're going to have u times v. That's going to be e to the x times sine of x. Minus the integral of v times du. So du is cosine of x, and v is e to the x. You might be thinking, well, Justin, you finally lost your mind. We can't really do anything with this. It's going to keep cycling from cosine to sine and then so on and so forth. We're never going to get a definitive answer. And you're partially right. I want to show you a really neat trick that's going to help us out with this a lot. So I want to remove the brackets. We don't really need those anymore. We're not multiplying by anything on the outside of the integral. So what are we trying to solve anyway? What is this all about? What is the integral we're trying to solve? That would be this one right here, e to the x cosine of x times dx. So I see this, and then I also see this. So we have the same thing on both sides of the equation. And this is one of those things that most people don't pick up on the first time, myself included. I had to have this concept explained to me like 2 different times before I got it, but one of my most brilliant students saw this right away, and I'm super, super impressed. That's like probably one of my proudest moments as a teacher. He said, well, wait, Justin, we can add this to both sides, and then we have a solution that works really, really well and really nicely. And yeah, like I said, I'm super impressed that he picked up on this right away. Most people don't, myself included. So let's go ahead and actually, before we do that, I'm going to make what we have on the left look slightly more like what we have on the right. So I'm going to put the e to the x before the cosine of x, just so it's more clear what we're trying to do. So I'm going to add this to both sides. You can always add an integral to both sides the same way you add a number or add a function to both sides of an equation. And my handwriting is getting worse and worse because I smell pizza, it's ready, and I'm hungry. So I'm sorry about that. So I'm going to leave this here, but then I'm going to write a new revised version of this equation below. So we have a little bit of canceling to do. Yoink and yoink. So now what we have is this. This is going to be 2 times the integral equals everything on the right side of the equation minus the integral we just took away. So it's going to be e to the x cosine of x plus, well, sorry, e to the x cosine of x plus e to the x sine of x. All right, and then one more thing we need to do is we need to divide everything by 2, because initially when we're given this problem, we know what we're setting out to find is this right here. We don't want to have the 2 there because the original problem doesn't have a 2. So we're going to divide everything by 2 to get the answer we're looking for. And once again, I'm going to do some rearranging. So we get the antiderivative, the indefinite integral of cosine of x dx is equal to 1/2 whatever appears on the right side of the equation. I'm actually going to factor out e to the x from both of those terms. So it's going to be e to the x over 2 when we divide everything by 2. In parentheses, I'm going to put sine of x first. It's going to be e to the x over 2 times sine of x plus cosine of x. And then, sorry, I'm OCD about the way things look sometimes, plus c. Well, I hope you guys found this useful, and I'll see you in the next video.